We're going to talk about something called, but better, partial fractions. Specifically, it's the integration of rational functions by partial fractions, if you want the long name. So essentially what we're going to do here is we're going to be given an integral, and it's going to be a rational function. So what's a rational function? Rational functions are fractions that are made of polynomials on the bottom. And now your first thought with these is, can we do our U substitution? In this case, it's not going to work out very well. There is a way to do it with partial fractions, but you're still going to have to split the fraction up, and then the second part, you're going to have to use partial fractions anyway. So might as well just start it from the very beginning. Now, an important thing here is that we want our denominator. If that's not true, then we want to do our long division to then separate it. So, for example, if we have some function f of x that can be written as a p of x divided by a q of x. If that numerator has a bigger degree, we want to be able to do that division to split it up into an s of x plus some r of x over that q of x. And now, so we would then focus on this part, and that part would just be a polynomial, and we could do the integral very easily. So that's going to be our key thing, is we need that top, though, to be a smaller degree than the bottom. And so since we're kind of stuck here, we can't use our U substitution. We want to go ahead and try to factor that bottom and see what we can do with it. And in this case, it's going to be an x plus 2, x minus 1. In our process of is to, well, normally if we have two fractions that were being added, we had common denominators and combine them. Partial fractions goes the other way with that. That we have a combined fraction here, and denominator over the x plus 2, and something over the x minus 1. And this is what our process of partial fractions is going to be, is converting from this left-hand setup to the right-hand setup. Because this right-hand setup is going to be that if you do your U substitution. So how do we do that? All right, so let's focus on here. It's going to equal something over the x plus 2 and something over the x minus 1. In order to make these two look alike, let's take, so this one with the a would need an x minus 1 over an x minus 1. The part with the b and then the bottom is an x plus 2, x minus 1. are the same. So they're not going to make any difference in helping to find A and B. What we're going to focus on are things that look different in this numerator. So let's set those equal to each other. And now we have to find our capital A and our capital B in some way, shape, or form. And there are several students think of doing it is to distribute the A and distribute the B. And then combine like terms. And then we can combine things together and make a system of equations that this A plus B is multiplied by X. So it has to equal to 1. This negative A plus 2B is a constant, so it has to equal 5. So A plus B equals 1, negative equals 5. From here, we can solve it in several ways. You could set up a matrix if you wanted to. You could do your substitution where you solve for an A or solve for a B in the first equation and substitute in. Or probably the best way for this example is do elimination of just let's just add the equations together. That our A's here are going to cancel. And then we're left B equals 2. Then plug that back in to A plus 2 equals 1. So A equals a negative 1. So our can be rewritten this way. And if you would like to split that up, you could. You can make that a negative integral of 1 over x plus 2. And then a 2 integral of 1 over x minus 1. Substitution with x plus 2 being your u, or x for the other one, x minus 1 being your u. And it'll be like a 1 over u is your integral. So it's a natural log. So it turns out to be a negative natural log, absolute value, x plus 2 natural log x minus 1 in the absolute value. And then don't forget your plus c. To it, there's some nuances we're going to get to a little bit later. But that's going to be our basic idea. Now, to go back, though, here's another way that you can do your partial fraction step of an x plus 5 equals a x minus 1 plus b x plus 2. Now, I like this second way better. I think it's a bit quicker. Usually, there are some situations where you'd be a little nuanced with picking your values, but in order to do this, if we only had one variable, either a or b, it would be very easy. So let's make my x equal 1. So 1 plus 5 would give us 6. But then in here, when x is 1, and we 3b, which b would then equal 2. Alternatively, if we try to get rid of this one, we could make our x equal to a -2. So -2 plus 5 is 3. That's going to be a -3a. Therefore, a equals -1. So this process of picking x values that will eliminate one of your variables is a neat little step. Let's do another one. So integral of, this one's a bit long, x squared plus 2x minus 1 divided by 2x cubed (3x squared minus 2x). Okay, top is 2, degree of the bottom is 3. Therefore, the denominator has a bigger degree. Let's go with what we got. So we would like to factor that bottom. All right, so factoring the bottom, well, first we should check if you would do a U substitution, is this going to work? Because U substitution is normally going to be the easiest. In this case, you can try it making your denominator your U to your DU. Does not give us what we need. So let's try and do our factoring. We don't need to factor the top. And in this case, but now the bottom, we can pull out an X. And then for the rest of it, it's going to be 2x and an x. And plus 2. So if you need to do your A times C method, when we do our integral, we want this to look like an A over x plus a B over 2x minus 1 plus a C over x plus 2. All right, so now we need to set this up. So it's an x squared plus 2x minus 1 over the x, 2x minus 1, x plus 2. And now we want to get our common denominators throughout these. So the A needs both a 2x minus 1 and an x plus 2. Then a B is going to need the x and the x plus 2. And then the C going to need the x and the 2x minus 1. Once again, we can ignore the bottoms and focus only on the numerators. And now you could go ahead and FOIL these and distribute the x's and then combine your x squareds, combine your x's, combine your constants, and then do your system of equations. But another way we could do this is making your x first equal 0. So -1 on this side times -1 times a 2. So -2a. This one will become 0. This one will become 0. So A is going to equal 1/2. 1, make your x equal to a positive 1/2, because that will get rid of this one. So 1/2 squared is 1/4, then plus 1 minus 1. So we get a b times a half times 2.5. So 5/2 times 1/2 gives us 5/4. Therefore, b is going to equal 1/5. Yeah, the bad thing with partial fractions is you often will get fractions. Then -2 is our last option. And we will get a 4 minus 4 minus 1. And then 0, 0, and then we're doing -2. So c times -2 times -5. So 10c. So c is going to equal. Now we need to set up. Is that order does matter. To go. Your B's go where they're supposed to go. Your C's go where they're supposed to go. They have to match up with the little expression, the fraction that you initially started with. Don't mix them up because that will change your answer. Do. First one is extremely straightforward. Next one, we have to do a little bit of a u substitution that 2x is going to influence things. So it turns out to be 1/10 natural log absolute value 2x minus 1. And that should be an absolute value. And then minus 1/10 natural log x plus 2 plus your c. Now, if you really using your laws of logarithms, this is the natural log of square root of x, 2x minus 1 to the 1/10 power, and then the other one's a negative, so it's going on the bottom, x plus 2 plus your c. Typically, though, we just leave it in this form. Doesn't really do too much for you. All right, let's try another one. So this one's going to have a few that we're going to need to address. Minus 2 plus 4x plus 1 all over x cubed minus x squared minus x plus 1. All right, the thing we have to notice here is that our numerator is bigger than our denominator. So we have to do our, or has a bigger degree than our denominator. So we have to do our long division. Synthetic division does not work in this case. So setting up our long division, here's a put your space holder in there. The cubes. X to the fourth. Multiply by an x. So now multiply this whole thing by that x. And then subtract. So we have to change all the signs. We get an x cubed minus x squared plus 3x, and bring that one down. Now, an x cubed turn into an x cubed. All right, well, that's 1. So we multiply this through. But then we need to subtract. So we change all the signs. As a degree smaller than what's out here. So this will be our remainder. So our numerator, or our fraction, can be rewritten as x plus 1, that's our quotient, plus our initial denominator. Okay, so now we need to do some factoring because this one's going to be very easy to evaluate. But what about this one? So let's take our denominator. And let's factor by grouping. Now I'm going to cut out that negative, but since we're factoring out a negative, we have to change that sign. So if you distribute that negative, we get back to where we started from. All right, here we can factor out an x squared. And now those two are the same. So we can go ahead and factor more. Pull that out. Down to there. So if you want to combine together, we get that. All right, so we have 4x over x minus 1 squared, x plus 1. Now here's one of our little nuances, that we're needing a over x minus 1. We're going to need a b over x minus 1 squared. So we're going to need to put that in there twice. Once for just the, if this was cubed, we would have another one for it being cubed over here. If it was to the fourth, we'd have another one for x to the fourth, or x minus 1 to the fourth. So whatever this exponent is, you're going to need that many terms with it increasing from just degree 1 to degree 2, degree 3, and onward. All right, so now let's get our common denominators on the right. We can skip the step of actually having the common denominators, or the process of getting them. And so we know what we need. From here, let's pick numbers that will help to get rid of some of our variables and make life easier. So let's make our x equal 1. B. So B is going to equal 2. We end up with the A's are gone, the B's are gone. It's a negative 2 squared times C, so 4C. So C equals -1. All right, so now we have a bit of help us to find just A, because we can't eliminate anything to eliminate A and B, or excuse me, B and C. We'll also eliminate the A. So we can pick any number we want. In this case, I would either pick a 0, because that's easy to deal with, or a 2, because that would make this segment a 1 and that segment a 1 to make life a little bit easier. Or you can pick whatever you want, but those will probably be your best. Let's go with 0. So 0 on this side, and then we're going to get negative A plus B, and then it's a -1 squared, so that's just a 1 plus C. So those added together give you 1. -1 equals negative A, so therefore A equals 1. All right. Over x minus 1 squared, x plus 1 can be rewritten as 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. Three easy integrals to evaluate. Now, the one thing to be careful of is that this one is essentially an x minus 1 to the -2nd power times 2. So we will not get a natural log with this one. But then our final answer is going to be natural log, absolute value, x minus 1, x minus 1 to the -1st, minus natural log, absolute value, x plus 1. And then plus our c. Now, if you want to, you can combine the let's do integral of 2x squared minus x plus 4. And on the bottom, x cubed plus 4x. All right, once again, our u substitution is not going to work. Always check that just to make sure. Because if u substitution is going to work, it's going to make your life a bit easier. Okay, so we have something unique here. In our denominator, one of our factors cannot be broken up into linear factors. It's an irreducible quadratic, at least over real numbers. So whenever we set up our equation here, We have our numerator always must be 1 degree smaller than the denominator. So whenever we have just something to the first power, we can just put a constant up top. But if our bottom is an irreducible, be a linear. But then our process is pretty much the same. We're going to get our common denominators. And then we're going to pick. So in this case, picking x equaling 0 is going to help out. So we know that our a is going to equal 1. But now here's where things are going to get a little bit more tricky. That it's going to be hard to find both. We're going to have to do a system of equations. And if you want to your distribution, this example is not too hard. We already know what a is, so that's going to make life a little bit easier. Or we could just pick 2 different x values, plug them in, and do our system of equations off of that. So multiple ways we can handle it. So we have an ax squared and a bx squared. And then we will have a cx only. And then just our 4a. So this is going to be fairly straightforward, especially because we already know what our a is, that a equals 1. So we will no longer need to worry about this part because we already solved that. And then it's going to be 2 equals 1 plus b, going with our x squared, so b equals 1. And for our c is going to equal just a -1 to begin with. All right. So over x plus x minus 1 over x squared plus 4. A bit of a difficult situation to handle. The first one's a natural log, so that's very straightforward. But how do we handle the other one? Let's squared. So we can combine fractions with common denominators. We can also split fractions that have addition or subtraction on top. All right. This next one, it's going to be a u substitution. So that's pretty easy. And this last one is going to be one of our arc functions. If you would get stuck on this, try to make your x into a 4 tangent squared, and then do some manipulation through there, and then have to convert back. So this will be a longer process. So just knowing your integrals would be easy. But then this will be a natural log of absolute value of x plus, when you make your u an x squared plus 4, the du would be a 2x dx. So you have that extra 2 to contend with. So it'd be a 1/2. minus arctangent of x over 2 plus c. Since it's an irreducible quadratic, our numerator here must be a bx plus c, or something x plus a constant. Let's go with another one. Very But we're not necessarily going to go ahead and solve it, but just so we get the idea of how we're going to handle different situations. So say we just have the integral of 1 over, let's say x minus 1 cubed, x plus 1, and then x squared plus 4 squared. I think that should cover all of our. So again, always break down your quadratics into linears if at all possible. In this case, x squared plus 1 is sum of squares, so therefore it's not going to be able to be factored with your real numbers. You have to bring in complex numbers to do it. So we're not going to. So now whenever we do our partial fraction, though, it's going to be an a over x minus 1, a b over x minus 1 squared, a c over an x minus 1 cubed. So we need to account for all of them. A d over an x plus 1. It's only in there by itself. And then an ex plus f over x squared plus 4. But now, since it's in there multiple times, plus h over the x squared plus 4 squared. To our integral, well, we would get our common denominators, make that big equation, selectively choose your x values to eliminate what you can, and find any values that you can. Oops, make sure that looks like an x. And it can be a long process when you have these big, long, cumbersome rational, but it's a fairly basic process of setting it up. And that's the important thing that we want to get across. After that, it's doing a bunch of just natural logs, maybe using a little u substitution to help you out. Sometimes you can do a u substitution, do that if you ever possibly can. And you might need to use an arctangent, something along those lines. So be aware of your ability or your possible ways of manipulating that.